In this video, we will have the proof of first isomorphism theorem and the second isomorphism theorem on rings with the help of the ideals. And to prove the second isomorphism theorem, we need to have this part. So, in this theorem, we have first isomorphism theorem and the second isomorphism theorem, and that is established with the help of this result. So the statement goes like this: if R and R prime are any two rings, and phi from R to R prime is an onto homomorphism with kernel U, then R prime is isomorphic to R mod U. This is your first fundamental theorem on homomorphism in the case of rings, similar to that of groups. And the second one says that there exists a one-to-one correspondence between the set of all ideals of R prime and the set of all ideals of R which contain U. U is nothing but the kernel. This correspondence can be achieved by associating an ideal W prime of R prime with an ideal W of R defined by. So how W is defined? That's defined in terms of W prime, and W prime is assumed to be an ideal in R prime. So again, this is also similar to that of lemma in section 2.7. So with W so defined, we need to show that R mod W is isomorphic to R prime mod W prime. So when we prove this, we'll have to bear in our mind how W and W prime are related. So only then it will be easy for us to establish this. So first we prove the fundamental theorem on homomorphism, on ring homomorphism, our first isomorphism theorem. Let phi from R to R prime be the given onto homomorphism with kernel U. So we know that how kernel is defined. So here U is nothing but all those elements in the domain of phi. So A in R such that the image of A under phi should be the additive identity of the codomain. So you have U being, this is nothing but the kernel of your homomorphism phi. So this is kernel phi. Now you define sigma from R mod U to R prime in this way. So again here this definition of this mapping is similar to that of your groups. So this has to be remembered how the function takes any element in R mod U to R prime. It is defined in this way. Sigma of A plus U is phi of A for every A plus U present in R mod U. Now being defined by us this rule, we have to show that this is well defined. So for that we will consider two elements of the domain to be equal, namely A1 plus U and A2 plus U. They are equal. So again this we keep mentioning that HA equals HB if and only if AB inverse belongs to H. So this result we are using in the case of rings also. This is established in groups. In the same way, proof can be established. Here we presume the result and we have the step A1 minus A2 belongs to U. Now we have to show that the images are equal. So we consider sigma of A1 plus U. So by this it is phi of A1 and sigma of A2 plus U is this. Right. Now when we consider phi of A1 minus A2, okay, see actually you have your job is to show that sigma is well defined. That is sigma of A1 plus U equals sigma of A2 plus U. So that is same as showing phi of A1 equals phi of A2. So that is same as phi of A1 minus phi of A2 equal to 0, and this. So this is what we have. Now how to get this from the assumption that is made. So we have considered A1 plus U to be equal to A2 plus U. So that gives us A1 minus A2 belonging to U. But U is nothing but this. So because A1 minus A2 belongs to U, phi of A1 minus A2 should be 0 prime. And but because phi is a homomorphism, we have this to be phi of A1 minus phi of A2. We have used both the properties of homomorphism with regard to the additive, with regard to the second one, that is A1 plus A2. This is the definition. But the property says that phi of minus A2 is minus phi of A2. So that is also used here. The definition as well as this, both are used. Definition and property. So you have this phi of A1 to be equal to phi of A2, and that is nothing but the image of A1 plus U under sigma, A2 plus U, image of A2 plus U under sigma. So elements in the domain are equal implies the images to be equal, and therefore sigma is well defined. Now because phi is on to, when we consider, see our mapping, sigma is from R mod U to R prime. So to show that sigma is on to, we need to consider an element R prime and capital R prime. R prime, any arbitrary element in capital R prime, we denote it as R prime. Now because phi is on to, for this R prime, phi is on to. It's from R to R, R to R prime. So when you consider R prime here, small r prime, it is present here, and because phi is on to, for this R prime, you will find one R in capital R, such that phi of R equals R prime. So the presence of R in R is confirmed, so definitely we will have our R plus U to be present in R by U, R mod U. So you have for R prime in R prime, this R plus U acting as the pre-image, so that your sigma is on to. So R prime equals sigma of R plus U, and that shows that sigma is on to. Now to prove that sigma is 1 to 1, we consider the images to be equal and show the pre-images are equal. But this is nothing but phi of A1, this is nothing but phi of A2. And taking this to the other side and using the property of homomorphism and the definition of homomorphism, we have this. And by the definition of kernel, this element should be present in the kernel, which is taken as U. And again, HA equals HB for only if. So here we mention that HA equals HB for only if AB inverse belongs to H. So here A1 minus A2 belongs to U. So that means A1 plus U should be equal to A2 plus U. So that shows that sigma is 1 to 1. Now to prove that sigma is a homomorphism, with regard to addition, with regard to multiplication, we need to establish these two conditions. Sigma of A plus U plus B plus U is sigma of A plus U plus sigma of B plus U. And similarly, for the product, sigma of A plus U into B plus U is sigma of A plus U into sigma of B plus U. So these two are to be established for sigma to be a homomorphism. So we consider the LHS of the first one, and remember sigma will function only if it is of the form sigma of an element in R plus U. So this should be an element in R. If it is in this form, it will not. So we simplify this further by the definition of addition in R mod U. We have this, and only if it is in this form, sigma will function, and it will take the element to phi of A plus B. And because phi is a homomorphism, you have this to be phi of A plus phi of B. But phi of A is nothing but sigma of A plus U, and this is sigma of B plus U. And in the same way, sigma of A plus U into B plus U, again it should be written in this form, only then sigma will function. But how from this that we get this? Because multiplication is defined this way in R mod U. And by the definition of sigma, you have this to be phi of AB. But phi being a homomorphism, you have this to be phi of A into phi of B. But this is the image of sigma, image of A plus U under sigma, and this is nothing but the image of B plus U under sigma. So you have your sigma satisfying both the conditions, and therefore sigma is a homomorphism. Now since sigma from R mod U to R prime is around 2 homomorphism, isomorphism rather, because we have shown 1 to 1 on to and homomorphism, R mod U must be isomorphic to R prime. Now to prove the second part, we need to have in the second part we have to establish a one-to-one correspondence between the collection of all ideals of R containing the kernel with the collection of all ideals of R prime. So to establish that, we prove these two results. First one is, if A is an ideal of R, then the image phi of A is an ideal of R prime. So to prove any subcollection of a ring to be an ideal, we have to know the description, and we have to show that it is non-empty, and we'll have to establish the criterion for that to be an ideal. But for an ideal, we have the conditions to be, first one is it should be a subgroup under addition, and then for every R in R, U in U, both RU and UR should be present. So these two conditions will come under criterion. So this already we have been mentioning that D and C is to be remembered for any subcollection to be a substructure of the given one or special substructure. Right, now first we have to show that, we have got the description here. We have to show that first it is non-empty. So now A is given to be an ideal, so 0 will belong to A. So that means phi of 0, which is 0 prime, it is present in R prime. So we have this 0 being a member of A, phi of 0 belongs to R prime, that is identity element, and that being present in phi of A is non-empty. So this 0 prime being a member of phi of A is non-empty. And then to prove that it's a subgroup under addition, so description over, non-empty also we have established, and for subgroup we have to consider two elements, phi of A and phi of B, any two elements in phi of A. So when we consider the difference, phi of A minus phi of B, because phi is a homomorphism, you have this, and your A, B are in capital A. When you consider these two, where are this A and B? They are in A. So A being an ideal, A minus B being a subgroup, it will be present in capital A. So the whole lot is a member of phi of A. So phi of A minus phi of B is a member of phi of A, and therefore phi of A is a subgroup under addition. Next we have to show that R prime for any R prime in R prime, and A prime in phi of A, R prime A prime belongs to phi of A, and A prime R prime belongs to phi of A. So you consider R prime into A prime, because R prime being a member of capital R prime, phi is on to, we have phi of R to be R prime. So R prime is replaced by this. And A prime belongs to phi of A means A prime can be written as phi of A, where A is a member of capital A. So this phi being a homomorphism, we have this step, and this belongs to phi of A. The reason is you have already your R to be present in capital R and A to be present in capital A, and A being an ideal, RA will be present in capital A, and therefore your phi of RA should be present in phi of A. And A prime R prime the same way, if you consider, this is what you get. Phi of A, same discussion. You have this. This is because again phi of A, A is an ideal, so both AR and RA are present in capital A, and therefore phi of AR will be present in phi of A. So phi of A is an ideal. Now in the second result, we established that if A prime is an ideal of R prime, then phi inverse of A prime is an ideal of R. and u is contained in phi inverse of A prime. Along with that, we are going to have phi of phi inverse of A prime is A prime. This later we need, so we include the proof of that also here. This is because your phi is onto. So whenever your phi is onto, you have this result to be true, not otherwise. Equality comes because phi is onto. So we'll prove these three. One is this phi inverse of A prime is an ideal of R, and U is contained in phi inverse of A prime. And along with that, we are going to establish this result, that is phi of phi inverse of A prime is A prime. Phi of phi inverse of A prime is A prime. So first we'll prove that this is an ideal and then come to this. Now first description we have got, then non-empty we have to prove. So when we consider 0 prime, because phi is homomorphism, 0 will be mapped onto, that is identity element will be mapped onto identity element. So you have phi of 0, this 0 prime to be. And this phi of 0 belongs to A prime because your A prime is an ideal. A prime is an ideal. So, but this in turn implies that whenever you have phi of 0 belonging to A prime, this by the definition of phi inverse of A prime tells us that 0 belongs to phi inverse of A prime. So, because 0 belongs to phi inverse of A prime, you have your 0 belongs to phi inverse of A prime, your phi inverse of A prime is non-empty. Next, to show that this is an ideal, we have to show that this is a subgroup under addition for which we consider two elements, say A and B, which means that phi of A and phi of B are present in phi of A and phi of B are in A prime. So when we consider the difference, because A prime is an ideal, it must be present in A prime. And this, because phi is a homomorphism, tells us that phi of A minus B, phi of A minus B, this is phi of A minus B belongs to A prime, because phi is a homomorphism. So this belongs to A prime. So when we have phi of A minus B belonging to A prime, we must have A minus B belonging to phi inverse of A prime. That is how it is defined, phi inverse of A prime. So this shows that the phi inverse of A prime is a subgroup under addition. Next, we have to consider an element R in R and A in phi inverse of A prime and show that both RA and A are present in phi inverse of A prime. Now, because R belongs to R, phi of R belongs to R prime, and A belongs to phi inverse of A prime, phi of A belongs to A prime. And because A prime is an ideal, an element from R prime and an element from A prime should be present in A prime. So phi of R into phi of A belongs to A prime, and same way phi of A into phi of R also present in A prime. Because phi is a homomorphism, this is phi of RA belonging to A prime, and therefore RA belongs to this. And in the same way, phi of AR belongs to A prime means AR belongs to phi inverse of A prime. So phi inverse of A prime is an ideal of R. Next, we prove that U is contained in phi inverse of A prime. So for that, you consider an X in U, which means because U is kernel, phi of X should be 0 prime. And A prime being an ideal, it's a subgroup, so 0 prime should be there in A prime. So phi of X belongs to A prime implies that X belongs to phi inverse of A prime. So X in U implies X belonging to phi inverse of A prime. Therefore, U must be contained in phi inverse of A prime. So now we prove the next part, that phi of phi inverse of A prime is equal to A prime. So for that we consider any y in phi of phi inverse of A prime. Then there exists one x in phi inverse of A prime such that y equals phi of x. So that is very obvious. So your y belonging to phi of x, y is equal to phi of x, and that belongs to, see, once you have this, where will be your phi of x? Your phi of x will be there in A prime. Your phi of x will be there in A prime. So we conclude that y, which is equal to phi of x, belongs to A prime. So y in phi of phi inverse of A prime implies y in A prime. Therefore, phi of phi inverse of A prime is contained in A prime. We shall name this relation to be 1. Then for any y in A prime, for the other inclusion, you consider y in A prime. Now since phi is on 2, there is one x in R such that phi of x is equal to y. For y in R prime, there exists one R because phi is on 2 and that y here considered as member of A prime. So phi of x is equal to y. So this implies that x belongs to phi inverse of y. So when we consider y, we have that to be y is what we have taken y to be phi of x. So phi of x, but where is our x? It is in phi inverse of y. So this phi of x will be present in phi of phi inverse of y, but that is contained in phi of phi inverse of A prime. So that is the reason for that is when you consider your A prime, you have y belonging to A prime and here your x is in phi inverse of y. So because y belongs to A prime only, we get this to be contained in phi of phi inverse of A prime. So y here implies y here. So we have this to be contained in this. So from 1 and 2 we conclude that phi of phi inverse of A prime equals A prime. This we need for the third part, that is the second part, there exists a one-to-one correspondence. So for that we will be using it. So you take tau to be collection of ideals of R containing U and tau prime to be ideals of R prime. We want to establish a one-to-one correspondence between these two. So we define a rule between these two as say theta taking any W to phi of W. Now from result 1 and 2 we have our theta to be well defined. Of course to some extent theta is on 2 also. Not to some extent, we have actually proved that phi inverse of any ideal in this tau prime. Supposing we consider that to be say A prime, then for this you have phi of phi inverse of A prime to be equal to A prime. So why this is considered here is for onto, so well defined. For any ideal here you will have, we proved in the first result that whenever A is an ideal, phi of A is an ideal. So you have given any ideal, you can associate with that an ideal in R prime. That's by first result just now we established. So well definedness is, comes from that first part. And for the second one, you consider any arbitrary ideal here to be say some A prime. Then what acts as the pre-image is phi inverse of A prime, because that also we proved that whenever in the second result we proved that whenever A prime is an ideal, phi inverse of A prime is also an ideal. So this is present in this, and not only that, U is contained in this, that is also established. So definitely this phi inverse of A prime is a member of tau. But now the question is it the pre-image of A prime? So how that can be established? Only when I consider theta of phi inverse of A prime. If I get back my A prime, that will tell me that this is the pre-image of, this is a pre-image of our A prime. So, but theta, how it is defined? It is defined as phi of phi inverse of A prime. Theta is defined in this way, phi of phi inverse of A prime. But phi of phi inverse of A prime is A prime. So you started with A prime in the codomain and you have got back, again you have come back to A prime. So by just mentioning that phi inverse of A prime is the preimage, you are able to come back to A prime itself. So your theta is on. Next, we show that this theta is 1 to 1, not phi. Theta is 1 to 1. So for that we consider the images to be equal. Theta of W is equal to theta of V. So that tells that phi of W is equal to phi of V. Now this is going to imply as that V is equal to W. How? If you consider x in W, obviously phi of x belongs to phi of W. But phi of W is taken as phi of V. So phi of x belongs to phi of V. But x belongs to, this implies that x belongs to phi inverse of phi of V. But x is in phi inverse of phi of V means you have your phi of x belonging to phi of V, which in turn implies that your x is in V. So your x belongs to V. X in W implies x belongs to V. And similarly, we can consider y in V to show that V contained in W. Phi of y belongs to phi of V, but phi of V equals phi of W. So we have this. So this implies that y belongs to phi inverse of phi of W. And this only implies that this is only contained in, it is not equal to W. As such, this is not equal to W, but this is contained in W. This is contained in W, and therefore your y belongs to W. So you have V contained in W, W already contained in V, so we have V equal to W. Therefore theta is 1 to 1. So since theta is both 1 1 and on to, there exists a 1 to 1 correspondence between tau and tau prime, and therefore we have the subdivision B. Now for the second isomorphism theorem on rings, we define a mapping, say psi from R to R prime mod W prime in this way. Psi of A equals phi of A plus W prime. So this rule being defined by us, we have to show that it's well defined, and that comes in this way because phi is well defined. When you consider two elements in the domain to be equal, A equal to B, then phi of A should be equal to phi of B. That's because phi is well defined. And this step, this is obvious, but this is nothing but psi of A, and the other one is psi of B. So you have your psi to be well defined. Now to prove that psi is a homomorphism, we consider psi of A plus B. We have to show that it psi of A plus psi of B. This is nothing but. But by the definition of psi, it is phi of A plus B plus W prime. And because phi is a homomorphism, we have this to be phi of A plus phi of B. This W prime is retained as such. And by the definition of addition in a quotient ring, this is rewritten in this way. But this is psi of A and this is psi of B. And in the same way for multiplication also, psi of AB is phi of AB plus W prime. That is by the definition of mapping psi. So this is phi of A into phi of B. This W prime is retained as such. And by the definition of multiplication in any quotient ring, this is what we have. So this is by the definition of multiplication in quotient ring. And this is nothing but psi of A, this is nothing but psi of B. So your psi is a homomorphism. Then to prove that psi is onto, we'll have to consider an arbitrary element. Psi is a mapping from this to this. So we'll have to consider an arbitrary element here as R prime plus W prime only. So for this R prime, because phi is onto, you will have one preimage R. So phi is onto. So since phi is onto, for R prime in R prime, you have R in R such that phi of R is equal to R prime. So for R prime plus W prime, we have that to be phi of R plus W prime. And this is nothing but psi of R. By the definition of psi, it is psi of R. So that proves that psi is onto. Now we need to calculate what that kernel psi is. All those elements which are mapped onto W prime. That is the identity element in the codomain, additive identity. So this psi of A by the definition is phi of A plus W prime equals W prime. So HA is equal to H if and only if A belongs to H. Using that, we have this phi of A belonging to W prime. But such a description we have already seen is for W. At the beginning itself, we mentioned that W is described in this way. So your kernel is W. Now, since psi is an onto homomorphism, it's the kernel W from R to R prime R prime mod W prime. By the first isomorphism theorem, R mod W should be isomorphic to R prime mod W prime. Now, in the next video, we will see the problems in this section 3.4. Thank you.